Welcome to my talk on the disordered Chinese restaurant process and other interacting growth processes. I'm going to report on joint work with Cécile from Bath and our joint PhD student Anna Senkevich. So the program of this talk is we have written a paper. Competing growth processes with random growth rates and birth times is the title. You can find it on the archive. And in this paper, we have developed a framework and a theory to study the extreme value behavior of interacting growth processes. And I want to advertise the technique developed in this paper, which has a broad range of possible applications on processes that are, in some sense, interacting and competing growth processes. And I want to do this by looking at one specific example, a disordered Chinese restaurant process, and to show you how our theory works and what it gives, what it yields in this particular example. So I start by showing you the classical Chinese restaurant, which is due to Jim Pittman. It's a process which has one parameter theta, bigger or equal 0, and it's best described by customers entering a Chinese restaurant. So the customers enter the Chinese restaurant one by one, and when the first customer comes, the restaurant is empty, and this customer sits at some table. Later, when the customer enters the restaurant, some tables will be occupied. So if at an occupied table, there is a number of customers Zj sitting there, and these are round tables. So if there are Zj customers sitting at the jth table, there are Zj available seats. So you can sit in between every neighboring pair of customers, and this is considered a different seat. So potentially these tables have an infinite capacity. So this customer enters the restaurant, and then she seats herself either at an already occupied table, and this is done in such a way that every seat at the table has the same every seat at all has the same probability of being chosen, and this probability is 1 over n plus theta. So theta is our parameter, n plus 1 is the number of the customer. She sits at a table with Zj customers with the probability Zj divided by n plus theta, because there are Zj seats, each one has a probability of 1 over n plus theta to be chosen. And if she does not choose one of these tables, she occupies a new table, and this happens with the remaining probability, which is 1 minus the sum over all the occupancy numbers Zj divided by n plus theta. Of course, all but finitely many of these Zj are 0, because only finitely many tables are occupied at every point in time. And the sum over the number of customers already sitting there is n. So this remaining probability turns out to be just theta divided by n plus theta. So this is the classical Chinese restaurant process. And now we disorder this process by distinguishing the tables. So the tables are not all the same, but there are nicer tables, maybe closer to the window with a better view, or whatever, and we model this by a fitness, Fj, so attractivity, some parameter Fj, which we take from a bounded interval, here chosen to be 0, 1, and when a table becomes occupied, we determine this fitness Fj. And then the new customer chooses the table not just proportionally to the number of seats available at the table, but also proportionally to the fitness or attractivity of the table. So in our new model, each seat at a table with fitness Fj is chosen with probability Fj divided by n plus theta. And again, the customer sits at a new table with the remaining probability, which is just 1 minus the sum of Zj, this is the number of customers, multiplied with Fj, the fitness of the table, divided by n plus theta. Because the Fj is between 0 and 1, this probability is also between 0 and 1. So this is a natural way to disorder this model, but there is one warning that I should put out. It's quite different from the original ordered Chinese restaurant process, or the process without disorder. Although this corresponds to fitness of all tables just being equal to 1 in this case, the crucial difference is that the probability of sitting at a new table, which is of order 1 over n in the model without disorder, is now of constant order. So we have a much bigger probability of introducing a new table at every step here. If you don't like this in the modeling, there are other models that don't have this feature. But here, I think this is interesting because this sort of increases the competition between tables, makes the model more interesting. So you can already guess where the competing or interacting growth processes are. You just if you just look at one table. Because the probability in each step that this table is chosen is of roughly or the probability of a seat in this table chosen is like 1 over n, and this is not summable. At every table will have an occupancy that, as time progresses, goes to infinity. So the occupancy of a table is a growth process, and of course, the growth of the different tables is interacting, because a customer can only sit at chooses one of the tables, and also there is a competition between tables on this basis. If I now ask a question like, what's the occupancy of the largest table at time n? I think this is a rather difficult question if you look at it just from the given model, because everything depends on the total configuration of tables at any time instance. So this is not easy to study this model. And our method is a way to study this. And before I show you the method, I'll briefly tell you what results we get for this particular example. So we assume, of course, that the fitnesses of the tables are an IID sequence, and mu is the name of the distribution. It's a sequence of values in 0, 1, and we assume that the essential supremum of mu is equal to 1. So the fitness is always less than 1, but it can be as close to 1 as you wish. And in this case, the behavior of this IID sequence, or of the maximum of the fitness, say, by the famous Fisher-Tippett theorem, there are 3 possible limit distributions for the maximum of the fitnesses up to time n, properly standardized. And 1 is our case A. This is when mu is in the domain of attraction of the Weibull distribution, so a properly scaled version of the fitness sequences, of the maximum of the fitnesses converges to the Weibull distribution. The second possibility is a domain of attraction of the Gumbel distribution. And the third possibility, the domain of attraction of the Fréchet distribution, cannot arise here because it is for unbounded distributions. Just to remind you, Weibull is exclusively for bounded distributions. Gumbel can be both bounded and unbounded. Okay, so we cover all the cases, although I must say that if we are in the domain of attraction of the Gumbel distribution, there are some mild technical extra assumptions that we are imposing that I'm not going to specify in this talk. So here's our first theorem, the asymptotics of the largest table. So if mu is, in both cases, domain of attraction of Weibull or Gumbel, so in case A or B, the number of occupants at the largest table at time n is not macroscopic. So if you take the maximum over the occupancies of all the tables I at time n, this is the ZIN, this divided by n, the total number of customers at this time, goes to 0. So this is different from the classical case where the order statistics of the table occupancy divided by n converges to a Poisson-Dirichlet distribution, which is what makes this very interesting. So here, occupancies are lower, and in both cases, we can say exactly how low they are, although I'm only going to state the result in the easier Weibull case, because there it's much nicer to state. And here you can see that there is a deterministic scaling function. Alpha, so the Weibull case is the case where the tail at 1 of the distribution is given by a regular varying function with an index alpha and a slowly varying part L, and these are the alphas and Ls that occur here in the in this scaling. And the limit is, that's funny, it's a Fréchet distribution. So this is the third type of extreme value distribution, the one for unbounded sequences. Okay, so under assumption B, there is a not so easy to state scaling and also a Fréchet limit. But the more interesting thing is, now that we know that the size of the tables are not of macroscopic order, so not of the same number of the same size as the number of customers, we still want to compare the largest and the second largest table, for example. And here is a very surprising theorem. If you look at the ratio of the most occupied tables, which I call Rn, so this is the size of the number of occupants on the largest table divided by the number of occupants on the second largest or second most occupied table. This random variable Rn converges in distribution in the following sense. The limit as n goes to infinity of the probability that Rn is bigger or equal x goes to 1 over x for all x or bigger or equal 1. And this holds both under the Gumbel or the Weibull hypothesis, although the proof is completely different in these two cases, provided by our very indirect method. I don't know of a direct way of showing this, and it seems, if you just wanted to address this problem, it's extremely intractable, I think. Without our method, I would not know what to do. And this is a very beautiful result. And it hints at some universality here, because the limit is independent of the distribution of mu. Now, how do we get these nice theorems? If you're experienced with discrete processes, then you might be familiar with the first step in our method, and this is embedding the process in continuous time. So this is a technique that's on the market for a long time, and this goes back probably to Carlin. It's been used, for example, by Svante Jansson in several papers, and it's, as we will see, a very beautiful approach if it works. So how do we embed our Chinese restaurant process in continuous time? Say T1 is 0, this is the time when the first customer enters, and say we know that at time Tn, which is a positive real number, the nth customer enters. At this time, we start n plus 1 exponential clocks. 1 of parameter 1 for each of the n customers in the restaurant, and 1 of parameter theta for the creation of additional tables. Tn plus 1 is then the time when the first of these clocks rings. And depending on which clock rings, we do different things. So if the clock corresponding to customer M, sitting at table J, is the first one to ring, then we toss a coin with success probability Fj, that's the fitness of the table this customer is sitting on. And if there is a success, this new customer, the customer coming at time n plus 1, joins this table. And if there is no success in this coin toss, the next customer sits at a new table. And also, if the additional clock is the first one to ring, the next customer sits at a new table. Okay, so this is an embedding in continuous time of our model, because to check this, you just have to check that the conditional probability of the new customer joining the table J is the same as it would be in the original description. And just to test this, we look at the probability that a new table is created at time tn plus 1. And this probability is given by the sum over the ratios of all the rates at which, by the ratio of the sum of all the rates at which this event happens. A new table is created. So this is the sum over all tables, number of customers times the probability that there is no success. And that's 1 minus fj, plus the rate of the extra clock theta, divided by the sum over all the rates, and that's just, as we see, we have n clocks of rate 1 and 1 of rate theta, so this is n plus theta. And if you use that the sum over the zj is n again, and then you have in the numerator n plus theta divided by n plus theta is 1 minus this term, and this is exactly the probability that a new table is created in the n plus first step. So this fits, and if you look at an individual table, the rate at which new customers join this table is given by the is always given by the number of customers times fj, which is the success probability of the coin toss. And this is the great strength of this approach. These are independent Ewell processes for every table. So this embedding in continuous time makes the growth processes of the individual tables independent. However, there is a price to pay, and this is the complexity of this embedding in continuous time, which depends on everything. And at the first glance, you wouldn't say that you can say very much there because of the strong dependence between the embedding and the individual growth processes associated with the tables. However, it turns out that if you just look at the process at which new tables, of introduction of new tables, this is a nice enough process that you can get some control over it. That is enough so that we do not need to understand the very complex dependencies between the growth of the table and the growth process of introduction of new tables. So if you, in fact, if you look at the number m of t of tables occupied at time t, this is a general Crump-Mode-Jaggers process with immigration. The immigration is given by a homogeneous Poisson process with rate theta, and the creation of tables happens by the unsuccessful coin tosser. This is a Cox process, so that is a Poisson process with a random intensity measure, and this intensity process behind this is given by the Ewell process y of t multiplied by 1 minus f, which is sort of the probability of no success in the coin tosser. So this is a complicated process, but for this process there is indeed some theory in the literature from the group of Peter Jaggers, for example, and this is such that we can have a law of large numbers that gives us the necessary control over the creation time of the tables. So this is the embedding in continuous time. And this allows us, and now I give you if I concentrate on the easier Weibull case. In this case, you can write down a function sigma t, which depends on the index of variation of our tail at 1, the slowly varying function, which is in there, and a t, which is derived from the martingale limit associated with our general branching process. So this sort of incorporates what happens very early, the randomness that comes from what happens very early in our process. That's not going to go away. And then we define a point process, where we sum over all the tables, and every table is sort of characterized by three components. The first one, tau(n), is the time of creation of this table in our continuous time scale, subtracted by this function sigma of t. The second one is the fitness, properly standardized. And the third one is the occupancy at time t of the nth table, again, properly standardized. And I want to emphasize that this factor here, this is very important, depends on t, but not on n. So the standardization still allows us to directly compare the third components. So here is a picture that sort of indicates what happens. This just shows the first two of the three components. So on the horizontal axis, there is time, and on the vertical axis, there is fitness. So every table is characterized by a point there, which is the time when it becomes occupied in our continuous time scale, and the fitness. Okay, very roughly, a table which is characterized by such a point has an occupancy which is comparable to the time remaining until time t and the fitness, because it grows with essentially with the rate given by the fitness, and as a Joule process does, and for a time which is the time spent between its creation time and the time t. Okay, so because the number of tables introduced here is a branching process, so exponentially growing there, the maximum of the fitnesses also is a growing curve. This is indicated here by this curve here, this here. And if you slide along this this curve and always compare the product of the height and the time until time t, you can identify a place, this is the sigma t here roughly, where there is the biggest chance of a successful table. So a table which is introduced at this time has a chance of being very fit and enough time left to grow a customer base. And then the scalings here indicate how big we have to choose a box around this point to have it, for the points to have a chance of being the largest table at time t. And this is has a distance to the maximum fitness value 1, which is of order 1 over t, and the width, which is of constant order. This corresponds to the fact that there is no scaling in the first component, so it's just tau(n) minus the distance sigma t to 0. And here this is 1 minus the fitness is of order 1 over t. Okay, and then we have this scaling for the size for the occupancy of the table. Okay, and this process here converges, and this is the theorem in our paper. This process converges to a Poisson process with an intensity measure in 3 components, which is given down below. And there's a sort of similar, unfortunately much more complicated result for the Gumbel case, and it's much more complicated because the scaling can also depend on n in the middle component, and there is also some scaling of the first component. But let's not go into these technical details. So the crucial thing is, what kind of convergence is this? So gamma t is a random point process. If you plug in a compact set from the underlying space, then the number of points under gamma t in this compact set converges in distribution to the number of points on this of this compact set under the Poisson process. Or in other words, you can use test functions, which are bounded functions of gamma t, which are continuous in the vague topology. This is the topology created by continuous functions with compact support. And for this compactness is very important that the space on which we work is sufficiently compact. So in this case, we have can compactify the first two components, and the third one can only be compactified at one place, because the total number, if it was completely compact on the reals, then the total number would have to converge, but the total number is m of t and clearly goes to infinity. So the compactification is such that we are allowed to use anything on the first two components and just have to look at the third component, and there is an escape point here at the zero for small families, but we're only or for small occupancy of tables, but but this is just right to study large occupancy. Okay, and now with this theorem at hand, we can we can find the largest or the most occupied table, which is, let's just say, which will be in the limit, the distribution will be in the limit, the point with the largest third component in this Poisson point process. And similarly, if you just look at the ratio, you can write the indicator that the ratio of the largest and second largest table is bigger than x, as this function of this point process. So you want you go over all the points. You want no points with the bigger third component, so that it's the largest, and no points between z over x and z, so that the second largest is sufficiently far away for this. And then you have this functional here is a bounded functional, which is continuous almost everywhere in the vague topology, and therefore you get as the limit an integral in terms of our explicit intensity function zeta. And although this is a complicated function, the scaling in x is what matters, and the scaling in x is found to be 1 over x. So this is indeed 1 over x. So this shows that this shows how our method gives these surprising results for the discrete time process by going via continuous time and producing this Poisson limit theorem on the points in an appropriately compactified space on this point process. And from this, we can get these results. And there are lots of other examples in the paper, so I invite you to have a look at it. And thank you very much for your attention at this point in time.